Well, hi everyone. I promised in class that I was going to show you how to solve a couple of problems in chapter 5 from the homework, and so I'm going to do that right now. One of the problems is number 7 in section 5.2. They give you a vector in R3, which is V, and it's the vector -3, 6, 1. And they're asking you to find an orthogonal basis for R3 that includes the vector V. Now, R3 is three-dimensional. That means I'm going to need a total of 3 vectors, one of which is V itself. Now, we have to come up with 2 more vectors. And by the way, there's lots of right answers to this problem, but the important thing is that the other vectors that we come up with need to be orthogonal to V. So if I would like to think about that, I could imagine the vector W having components maybe A, B, C. And because that vector needs to be orthogonal to V, it just means that when you do the dot product of the 2 vectors, which is what I'm doing right here, I'm taking the dot product of V and W, or in other words, the inner product. Just using the standard dot product, right? We would get this equation right here. Now, it's easy enough to find values of A, B, and C that would satisfy that equation, and that would give us a second vector for our basis. And in fact, I would recommend that we just go ahead and do that. So for example, I could choose, we can just do this by eyeballing it. Okay, we don't have to like go through a whole matrix and solve it by back substitution. I can just eyeball it, and just looking at it, this is not the only answer. But I can see that if A is equal to 2 and B is equal to 1 and C is equal to 0, that we get a vector that we can use. So let's make that the second vector in our basis. That would be the vector 2, 1, 0. Okay, so we're 2/3 of the way there. And you can just check really quickly that, when you dot V and W together, you do get 0. So how do we get a third vector that is also orthogonal to both of these 2? Well, there's actually more than one way to figure this out. One option is to, again, create another vector. Let me call it, I don't know, maybe I'll call it U, which would be, again, I can choose A, B, C here. And if I dot the vector U with either of the other 2 vectors, I should get 0. So this time, I would actually have 2 equations that would both have to be true if I'm trying to find a third vector that is orthogonal to both of these 2. And what you can do here is you now can write down an augmented matrix for this system, and you can solve it for A, B, and C. Actually, the other thing you could do is just pick some numbers. Like I could just pick B to be equal to 1 right here. That'll tell me what A is equal to. A would have to, actually, let's do this. Let's pick B to be 2. And then A would be -1, right, based on the second equation. And then putting all of that information into the first equation, if A is equal to -1, and if B is equal to 2, I get 3 plus 12 plus C is equal to 0. And so C would have to be -15. And so my third vector here could be the vector -1, 2, and -15. So these 3 vectors together will be an orthogonal basis for R3. This is one correct answer. You can check that if you dot any 2 of them together, that you do in fact get 0. And you can also, so you can check, V.U, V.W, U.W, right? All of those are going to be 0. So that's one way to do it. Another way to do it, maybe you like this even better, is this uses something that's not really from Math 250B, but once you have 2 vectors, if you're looking to make another vector that is perpendicular already to 2 vectors that you have in your hands, an easy way to do it is actually to use something that you learned in Calc 3, which is the cross product of the vectors. If you cross two vectors together, you will create a third vector that is orthogonal to both of the two vectors that you started with. So here we already have two orthogonal vectors, and we can make a third one that is orthogonal to both of these by just taking their cross product. That's probably the fastest way to do the problem. So I'll leave it to you. There's lots of right answers here. You can either just eyeball the vector W that you can see clearly that it's orthogonal to V just by the dot product here, and then cross the two vectors together to get a third vector. Or you can set up a third vector of the form ABC and dot it with each of the vectors V and W, thereby creating a system of equations, and then you can solve that system for the unknowns. Take your pleasure, whatever you'd like will work. Yeah, and so the other problem that people have been asking me about is number 15 from section 5.2. And a lot of what's maybe bothering people with this question is just there's a bunch of language in the text that actually, for the most part, is irrelevant to what you're being asked to do here. First of all, the vector space. The book is emphasizing, they're calling it C0 from -1 to 1 rather than just, C of AB like I've normally been doing. This really just means continuous functions defined on -1 to 1. And we're going to use the inner product that we have so often been using. I'll just write it here. The inner product of f and g. It's going to be the integral from -1 to 1 of f of x times g of x times dx. Okay, so we're going to start with that. And what we're being asked to show, guys, is basically to show that these three functions are orthogonal. You don't need to worry about all of the rest of the stuff they're talking about, Legendre polynomials as solutions to a differential equation. That's not really what this problem is about at all. Let's just focus on checking that F1, F2, and F3 forms an orthogonal set. Guys, we're just going to have to do some integrations, right? We're just going to have to calculate, okay, the inner product of F1 with F2. Okay, so this is by the formula. This is just the integral from -1 to 1 of F1 times F2, which is 1 times x dx. Okay, we just have to integrate that. All right, that's 1/2 x squared. When you evaluate that from -1 to 1, you get 0. You can put a check on that. Okay, then we do the same thing with F1 and F3. Again, we have an integral from -1 to 1 of F1 times F3. This is 1/2 times the quantity 3x squared minus 1 dx. And we can pull out the 1/2. And when we integrate 3x squared minus 1, we'll just get x cubed minus x. And when you evaluate that at the upper and lower limits of integration, you again will get 0. You don't need to show a huge amount of work for any of this. The integrals are really pretty easy, actually. And then finally, we have to do the inner product of F2 with F3. This will be the integral from -1 to 1 of F2 times F3. Now that's going to be 1/2 x times 3x squared minus 1 dx. And in order to do that integral, I would pull the 1/2 out in front, but I would also just multiply the x through the equation. So this will become the integral of 3x cubed minus x. And now I actually have to do this antiderivative, okay, but it really isn't too bad. You're just going to get 3/4 of x to the 4th minus 1/2 of x squared. And again, when you evaluate that from -1 to 1, because the powers of x are even here, they're all even, then what you get when you plug in 1 and what you get when you plug in -1 are going to be the same, because you're raising these values to an even power. When you raise a number to an even power, it doesn't matter whether it was a positive or a negative to begin with. So again, this is also just equal to 0. No big deal. Okay. The next part of the problem is they do ask you, once you know that it's an orthogonal set, they ask you to verify that it is, or sorry, they ask you to construct an orthonormal set. This means we need to find the norms of all of the vectors and divide through by those norms in order to normalize the vectors here. So I'll do the first one or two of these. It's really, again, just integration that we have to carefully take care of here. So like, if I want to know what is the norm of F1, well, the norm of any vector is just the square root of the inner product of that vector with itself. So the square root of the inner product of F1 with F1. And this would be the square root of, well, the inner product is the integral from -1 to 1 of f of 1 times f of 1, which is actually just 1 times dx. And when you do this calculation, you simply get radical 2. So it's easy to integrate dx. You just get x. And when you evaluate x from -1 to 1, you get 2. So that all goes under a radical. Maybe I'll just summarize that over here. So the norm of F1 is radical 2. Then I have to do the norm of F2. Okay, so again, nothing tricky about it at all. We just have to be patient when we do the calculation. This is the square root of the inner product of F2 with itself. And so underneath the radical, we will be doing an integral from -1 to 1. F2 times itself is literally just x squared. And so now I just have to do the antiderivative of that, which is 1/3 of x cubed. I'm going to evaluate that from -1 to +1, and that becomes the square root of 2/3. Okay, so again, I'll record that over here. The norm of F2 is radical of 2/3. Okay, great. And then finally, we have to do F3. And this one's the messiest one, but the concept is, of course, the same. The norm of F3, well, that's going to be the radical of the inner product of F3 with itself. All right, so underneath that radical, we're going to be integrating from -1 to 1 of F3 of x squared. So this is a little bit annoying. I have to square this thing. 1/2 squared is 1/4. And when I square out, I'm going to go ahead and do this right now. I'm going to square out the 3x squared minus 1. I'm going to FOIL that out. I'm going to get 9x to the 4th minus 6x squared plus 1. Okay, so a little bit of patience is needed here to get that all correct. And now underneath this radical, I can pull the 1/4 out of the integral. And I'm going to just go ahead and integrate each term here. I'll get 9/5 x to the 5th minus, I guess it'll be 2x cubed, and then plus x. These are all going to get evaluated between -1 and 1. Okay, so one more step. I've got to kind of clean this up a little bit. I have a square root of the quantity of 1/4. Now, when I plug in 1 and -1 and do the subtraction, I'm actually just going to double all of the coefficients. So 18/5, and then -4, and then plus 2. This is what I think we should get. All right. And then this can probably be cleaned up a little bit better even than that. 18/5 minus 4 plus 2. Let me just simplify that. That's 18/5 minus 2. Right? Combine the 2 and the 4. And that's 18/5 minus 10/5, which is 8/5. So it's actually radical of 8/20 if I clean that up. And I can divide out a factor of 4 from the top and the bottom of that. And I just get the square root of 2/5. Okay, so that's the norm of F3. It's the square root of 2/5. And so finally, once we have the norms of the vectors, F1, F2, and F3, we can go ahead and make our orthonormal set. Because remember, to do the orthonormal set, we just take our orthogonal set and we normalize each vector. So I take the first vector, I divide it by its norm. Right? Then I take the second vector, which is x, and I divide it by its norm. Okay, and then finally I take the third vector, which is 1/2 of 3x squared minus 1, and I divide it by its norm. And there you have it. No need to clean these answers up. If you really check in the book, you'll see that they tried to do that. You don't have to do that here. This is the whole point of the problem, really, is what we've already kind of shown here. So anyway, I hope that makes sense. It's the usual process of orthonormalizing a set. Once the vectors have been shown to be orthogonal, we just have to divide by their norms. It was a little bit of work to get the norms because we had to do this integration formula to do those calculations. But once we have those norms, we just divide by those norms and it makes everybody into a unit vector. That's how it works, guys. I hope it makes sense. Feel free to follow up with me, though, if there are any lingering doubts or questions about it. I'll certainly be glad to clear it up further. Thanks for taking the time to watch this. I hope that it helps you kind of get moving on the homework a little better. And I'll look forward to seeing you guys again real soon. Bye for now.